Deep learning has significantly transformed the landscape of generative modeling, opening up new horizons for innovation across various fields. Today, we will delve into the applications of deep learning in generative modeling, specifically focusing on powerful techniques like variational autoencoders, or VAEs for short, and how they utilize random numbers to generate complex and realistic data samples. So far, we've learned about generative models, which are fascinating tools in artificial intelligence and machine learning that enable the creation of new data that resembles existing datasets. We've explored how these models function, particularly highlighting generative adversarial networks, yes, those GANs that you've probably heard about, and variational autoencoders. They each generate images and data through their unique processes. We also touched on their applications in natural language processing, such as utilizing the GPT-2 model to generate coherent text based on prompts. Overall, generative models open up exciting avenues for creativity, data augmentation, and automation across various fields. Now, we will cover several applications of deep learning within generative modeling, spotlighting how VAEs can efficiently create realistic images and complex data structures. Along the way, we'll even look at some coding examples to see these concepts in action. So let's jump right in and discover how deep learning continues to push the boundaries of what's possible in generative modeling. The included figure, titled Applications of Deep Learning in Generative Modeling, presents a pie chart breaking down 5 application areas with their respective shares. So we see variational autoencoders, or VAEs, taking the largest slice at 30%, followed closely by generative adversarial networks, or GANs, at 25%. Then we have text generation, like GPT, contributing 20%, while image generation, such as Midjourney, accounts for 15%, and data augmentation rounds out the chart with 10%. Now, some key patterns really pop out here. VAEs represent the largest share, which shows us a notable emphasis on those latent variable methods in the applications surveyed. GANs coming in second highlights their ongoing importance for high-fidelity generation tasks. When we combine the shares of text and image generation, it accounts for a solid 35% of the whole distribution. This tells us that generative modeling is making serious strides across both text and images. Text generation alone is a substantial portion, reflecting just how rapidly those transformer-based language models are being adopted. Now, data augmentation, although it's the smallest slice at just 10%, is still an essential application that supports downstream supervised learning. So, when we look at these proportions, we can conclude that the field relies on a combination of complementary techniques. The latent variable models like VAEs and adversarial approaches, such as GANs, are dominating. Plus, sequence and multimodal generation are playing major roles, while practical uses like augmentation remain critical for bolstering real-world datasets. What this distribution suggests is that practitioners should really consider both the task requirements and the unique strengths of each approach when choosing a generative method. Generative modeling primarily serves the purpose of creating samples from learned distributions, which can be both intriguing and useful. Let's focus on variational autoencoders, or VAEs, which have really caught on thanks to their ability to generate diverse and high-quality data. So, what exactly are VAEs? Well, they take a fresh approach by mixing neural networks with variational inference. A powerful statistical technique that helps us approximate complex distributions. Now, the architecture of a VAE consists of 2 main parts, the encoder and the decoder. The encoder compresses the input data into what we call a latent space, capturing the essential features of that data while throwing away the unnecessary noise. Then the decoder comes into play. It takes samples from this latent space and reconstructs the original input. Pretty cool, right? By doing this, the model learns to generate new data points that resemble the training data. All right, let's illustrate this with some code. Now, let's implement the encoder and decoder for our variational autoencoder, or VAE. First, we'll start with the encoder class, which is really quite fascinating as it takes a flattened image, typically that's a vector of size 784 representing a 28 by 28 image, and it maps that through a fully connected layer to create two outputs, the mean and log variance of the latent space. This step is crucial because these two parameters, mean and log variance, actually define the distribution from which we're going to sample during the generation process. To add a bit of complexity here, we use the ReLU activation function in the forward method, which helps introduce nonlinearity, allowing our model to learn more intricate representations. Now, moving on to the decoder class, this part's designed to reconstruct the original image from the latent representation that we sampled from the encoder. It's similar to the encoder, but it works in reverse, expanding the latent representation back to its original shape using fully connected layers. And we come to the last layer, which employs a sigmoid activation function. This is really important because it ensures that our output pixel values are nicely constrained between 0 and 1, making it perfect for handling our binary data like the MNIST images we often work with. With this setup, we're establishing a robust framework for learning effective encodings and performing data reconstructions, both of which are essential for generative modeling. Now let's implement the core variational autoencoder, or VAE model, which effectively combines our previously defined encoder and decoder. In this implementation, we inherit from nn.module, allowing us to utilize all those awesome functionalities provided by PyTorch. The __init_ method is where we initialize the VAE class. And here, we instantiate both the encoder and decoder as its components. Next, we need to introduce the reparameterization trick through the reparameterize method. This technique is really crucial, as it enables us to generate samples from the learned latent space while still preserving the ability to compute gradients for backpropagation. So, this method takes the mean, or mu, and the log variance, or log var, that our encoder produces, calculates the standard deviation, and samples from it using a random tensor. What we get out of this is a latent representation of our input. Now, let's go ahead and see how we can implement the forward method, which processes an input tensor, x. The method starts by calling our encoder to obtain the mean and log variance. Using these, we then apply the reparameterization trick to get our latent variable, z, which is then passed off to the decoder. This allows us to generate the reconstructed output alongside the latent variables we use for loss computation. This structured flow we've built enables effective learning and the generation of data samples. Next, we will define the loss function that is crucial for training our variational autoencoder, or VAE. This function brings together two essential components, the reconstruction loss and the Kullback-Leibler, or KL divergence. So, let's break it down. The reconstruction loss is computed using binary cross-entropy, which essentially compares the output generated by our decoder to the original input. This loss helps us gauge how well our decoder is doing in terms of, accurately reproducing those input images. Now, alongside this, we also calculate the KL divergence, which is really important. This component regularizes our model by making sure that the distribution we learn within the latent space closely matches a standard normal distribution. We achieve this by applying a penalty that considers how much the learned mean and variance deviate from the expected values. Finally, we combine both losses, which gives us a comprehensive measure that encourages our model to not only reconstruct effectively, but also to learn a meaningful latent representation. By optimizing this loss function during training, we steer the VAE toward generating coherent, realistic data samples. Now, let's implement the training loop for our VAE model. First, we set up the training parameters, which include batch size, learning rate, and the number of epochs. After that, we define a transformation for our MNIST dataset to ensure the images are converted to tensors and normalized properly. We load the training dataset using PyTorch's dataset utilities, and then we create a data loader to help with batch-wise processing during training. Next, we initialize an instance of our VAE model and set up the Atom Optimizer with the model parameters. In the training loop, we iterate through each epoch and make sure to set the model to training mode. For every batch of training data, we first reset the gradients of the optimizer to prevent any unwanted accumulation. We then pass the batch through the model, and it returns the reconstructed images along with the means and log variances of the latent variables. The loss function, which includes both reconstruction loss and KL divergence, is computed, guiding us in how well the model can generate outputs that resemble the original inputs. We backpropagate this calculated loss, updating the model's weights based on the gradients. After each epoch, we print the loss value to monitor the model's performance over time. This allows us to observe its learning curve and effectiveness in minimizing the loss. Now, let's implement a function that will allow us to generate new images from our trained variational autoencoder, or VAE. This function, GenerateImages, takes in two inputs, the model and the number of samples you want to create. First off, we need to set the model to evaluation mode, which we can do with model.eval, ensuring that any dropout or batch normalization layers behave properly during this inference step. Next, we're going to use torch.noGrad to turn off gradient calculations. This speeds things up since we don't need those gradients when generating new images. Now, within this block, we'll sample random points from a standard normal distribution. We do this using torch.rand, and we create a tensor called Z that represents our latent space. The dimensions of this tensor will match the number of images we want to generate, with each point having a dimensionality of 20, which aligns with our VAE's latent space. After that, we'll pass these random samples through the decoder to create new images. Finally, we reshape the output so that it matches the original image dimensions of 1 channel by 28 by 28 pixels, which is perfect for the MNIST dataset. So, by calling this function and providing the model along with the number of desired samples, we can get a fresh set of images that showcase the model's ability to create new variations inspired by the training data. The applications of VAEs extend far beyond mere image generation, and it's fascinating to see how versatile they can be. They can be utilized in various domains, including medical imaging, where they can generate synthetic medical images, which is so cool, to augment datasets for training purposes. VAEs are also instrumental in anomaly detection. They enable us to identify those abnormal data points that deviate from normal patterns, which is really crucial in many applications. Moreover, they facilitate smooth transitions in latent space. This allows features like interpolation between different data samples, helping us gain insights into the relationships within the data. It's a really powerful concept. Now, consider leveraging VAEs to generate new samples for training machine learning models, especially when real-world data is scarce or, let's face it, pretty expensive to collect. By synthesizing these realistic data points, we can create robust datasets that bolster our model's performance, ensuring they maintain accuracy even when they're in deployment or production. This capability can really make a difference in how our models perform in real-world scenarios, don't you think? As we wrap up our exploration into the applications of deep learning and generative modeling, specifically with VAEs, it's clear that these innovations have opened exciting possibilities across numerous fields. The ability to generate new and realistic samples holds promise for advancing research, creativity, and efficiency. We've demonstrated how VAEs work alongside some hands-on coding examples, illustrating how to implement them from scratch and generate unique outputs based on learned data distributions. Now, deep learning techniques like VAEs aren't just theoretical exercises. They offer practical, impactful solutions to real-world challenges. So, whether you're a programmer, a data scientist, or an artist looking to enhance your creative process with AI, generative models are definitely poised to play an essential role in shaping the future. The journey doesn't stop here. As you continue to explore the captivating intersection of deep learning and generative modeling, there are endless possibilities just waiting to be uncovered. So keep that curiosity alive.